All right, so welcome again, everyone. Okay, so let's get started. It's been around 3 minutes. And by the way, my goal for today's lecture is hopefully we can get it around 1 hour or at most 1 hour, 30 minutes. So that's going to be my goal. But we'll see how long it takes, and yeah, we'll take our time. Okay, so one more time, welcome everyone. Today we're going over Calculus BC. Yes, this is being recorded. And then I'll give some more information about where you can get the recordings and things like that. Just in the next few slides. All right, so Calculus BC Unit 9 review. That's what we're going over today. My name is Kyle, also known as Jelly the Octopus. And yeah, so it's pleasure meeting you all through the screen. And then let's get started. So just curious, is anyone here not familiar with 5 Hive? Just curious if some people aren't familiar, I'd be happy to go over the organization I'm part of, but if most of us are familiar, then we can skip over this slide. So if you could, yeah, I'm sure we all love 5Hive. So again, is there anyone who hasn't heard of 5Hive? Just last check. If not, we'll move on. Yeah, 5Hive is fire. Okay. Anyways, you can just take a look at this slide to get an idea of what we do. In a nutshell, we provide free AP resources for students like you by students. And so that includes practice tests and lectures like these that I'm hosting today. All right, let's get into the content then. So again, Unit 9 is going to be on parametrics, polar and vectors. Sorry, I'm just double checking. Yes, I have my recording going. Okay. So yeah, these are the three big ideas of this topic. Okay, so before we get into the actual content, I just want to introduce how this lecture is going to go. So how I've structured today's lecture is for each topic, I first have a summary slide just of the main ideas and things to remember and go over. And then I have a sample problem, or maybe two for each topic. And then we just move on to the next topic. So that's how this lecture is going to be structured. And feel free to ask questions during any part of today's lecture. I'm going to be monitoring the chat, so the lecture channel number 3 chat periodically. Feel free to message there. And I think we may have some other people who might be able to answer questions, but regardless, I'll be checking periodically. And then these two links are more for me for demonstration later. And then, yeah, here are just a few important links. So first, this survey link. And okay, yeah, reading has already sent it. So just please fill out that form whenever you leave today's lecture. So even if you can't stay for the entire time, please do fill out the form. It just asks some basic questions so I can improve as a lecturer, and then also just some more data for 5Hive to make these events better for you. And then also here I have the link to all of our 5Hive lectures, so please let me know if you can access that or not. So I believe that's this spreadsheet here. So you can see we have all of our different topics and units that we're covering. For example, if I scroll to A, B, and BC, you can see we have some of our recordings here. So this is one of my recordings from a while ago. So you should be able to find all our recordings and slides here. It just may take a few, I think typically it takes a few days for us to update everything. So yeah, just keep an eye on that. And without further ado, that's all I have for our overview. So hopefully there aren't any questions here, but if so, please ask. And then, yes, so moving on, we can go over the actual content of today's unit. So first we focus on our parametric equations. So taking our derivatives of parametric equations, finding arc length, and then we move on to our vector value functions. So integrating vector value functions and solving motion problems with both parametric and vector value functions. And then finally, we end off with our polar functions and polar coordinates. Sure. yeah, I guess I would recommend watching the recording if you can't focus now. Um, and well, I mean, I would hope you can take as much as you can from right now, but the recording is always there for you to review. Okay, and yeah, so I was talking about polar coordinates, so taking the derivative of our polar functions and then finding area of single polar curves as well as regions bounded between two polar curves. Yes, all lectures are recorded. And the lecture schedule 2025, that spreadsheet will eventually have all our lectures. And also we have a YouTube channel. I'm sure you can find it somewhere, but we're also uploading our lectures there as well. Maybe I can send that link later on for you all. Okay, so before we get started, I'm curious, are there any topics that yeah, I think one of mine were the first to be uploaded to our channel. So I'll send the link to the channel in a little bit. So for these topics, does anyone have any requests for ones you'd like me to go over first? Yeah, and Reading has sent the uh, YouTube channel. Okay, 9.1, and then 9.7, 9.8. Any other requests? Okay, so some are... Okay, so it's a bit hard to satisfy everyone. I think most people want us to go over the polar topics first, so hopefully that's okay with everyone. Yeah, so I'll start with 9.7 and finish all these polar topics, and then we can come back to the parametrics and vector value functions. All right, so in that case, let me get to 9.7. Okay, and slideshow. All right, so our first topic for today is going to be defining and differentiating polars. So most of our calculus techniques for real valued functions, so functions in our Cartesian plane, can be extended to functions expressed in polar coordinates. So basically, a lot of what we already have learned in previous units can be applied to polars in the same way. So if we have a curve that's defined in this form, so we have our r is equal to the function of theta, we can analyze our derivatives of our polar function. We can also convert to a parametric form if we, so we're basically converting back to Cartesian coordinates, and instead of time, it's a parametric in terms of theta. So these are our relationships between the Cartesian coordinates and the polar coordinates. And then as a reminder, our first derivative in terms of our Cartesian coordinates is in this format. So if you recall, this is the same as our parametric derivatives. And then our second derivative, again, is the same format as our parametric second derivatives as well. And then all of these pieces of information will tell us about our slope, concavity, and the overall behavior of the curve in a polar form. So make sure to be reviewing what these different ideas tell us. So what do the derivatives tell us? And yeah, those are all things that we review in previous units. Okay, so are there any questions about anything on this slide so far? If not, let's all try to solve this question. So feel free to attempt this on your own, and then feel free to let me know what you get in the chat. So just to give you an idea of how I've structured these sample problems, the main problem is up here, and then these sub bullet points are just some hints and some guiding questions if you need them. So for example, in this problem, we want to find our derivative in terms of dy and dx at this point. So some tips would be to first convert to our parametric form. So again, that's basically converting it back to Cartesian points. And then we also want to find our derivatives of dx in terms of d theta, dy in terms of d theta, then use our parametric formula for the first derivative. All right, so we got one answer in the chat. So Sage, I'm not too sure if that's the right answer, but um, yeah, I can't recall the exact answer either, so we'll see. We'll find out together. And yeah, by the way, for those of you um, who are solving the problem, if you could just let me know once you've solved the problem, even if you don't want to share your answer. That way, I'm just not waiting too long and wasting all our time. So just give me a heads up whenever you think you're ready for me to move on to the solution. And okay, so one person's ready to move on. Maybe if we can get a few more people, that would be great. But again, take your time. There's no rush. And okay, a few more people. Okay, so let's move on, and hopefully you are able to at least get through part of this question. So hopefully we can just see if your thought process was correct at least. Okay, so I apologize for the formatting. I should probably use latex or something, but hopefully we can understand at least a little bit. So our final answer should be this value, so -2/7 square root of 3. Is that what you guys got? Because it's possible I made a mistake somewhere, so please always let me know if there's any mistakes. Anyway, so our first step is to convert back into our parametric form, so in terms of x and y. So if you recall, our formula is r times cosine. So we can substitute r to get this expression, and then for y, similarly, it's r times sine of theta. So we can substitute our expression for x, sorry, for y. Okay, so the question, how do you find x of 0 and y of 0? Yeah, hopefully, so I'm not sure if you, okay, cool. Yeah, by the way, these are thetas, not 0, just to make sure that's clear. And one more time, how I got these expressions were just by plugging in our value of r, our function of r, into this equation for our x and y forms. And then once we, okay, cool, reading has added the latex, very nice. And yeah, so after we have our x and y, so we can take our derivatives in terms of d theta. And so you should get these expressions. Sorry, I didn't show all my work, but once we get these two expressions, if you recall our dy dx, we can just divide dy d theta divided by dx d theta. And if we plug in pi over 3, we should get this value. When is the product rule? I may not have shown it here. Yeah, do you want me to solve this out for you, or is it okay if you try your... Oh, okay. Well, I think you would use the product rule when you take the derivative. Yeah, and reading has sent a nice reminder. Yeah, so here you have two choices. You can just take the derivative here and use the product rule, or alternatively, you could multiply this out, and then you would just have a product rule for the cosine theta times sine theta. So hopefully that answers your question. Hopefully. Okay, cool. And so if there aren't any other questions, let's move on to the area of a single polar region. All right, so for a polar curve given by a function in terms of theta, our area function is going to, sorry, our area formula is going to be this. So area is equal to 1/2 integral from a to b of f of theta squared d theta. And basically this is calculating our area swept by the curve as theta moves from a to b. That's just a fancy way of saying the area underneath this curve. But yeah, that's why we want to use the word swept instead of underneath, because it's in relation to our origin point. So it's not exactly under, so under in quotes, but it's a similar idea. And yeah, so I won't go over the proof for this formula, unless if you guys want me to, I can, I think I still remember it, but basically, if we take the sum of these arcs, so you can see this arc, purple arc here, if we, so it's similar to the idea of Riemann sums, where instead of adding a bunch of rectangles together, we're adding a bunch of arcs together. And then if you do a similar approach to Riemann sums, you should end up with this formula. So hopefully everyone is okay with this area formula. And if so, let's try this sample problem. So we have a polar curve. Our theta equals 1 plus cosine theta. And we want to find what is the area enclosed by one loop of this polar curve. And then some hints. So what are our limits of integration? That's the first step in our problem. And so yeah, when we take our integral, we may have to use some special relationships in order to make our lives easier. So hint, what is cosine squared of theta equivalent to? So this will help you when you go and solve this problem. So yeah, let's all attempt this, and then again let me know once you're ready. And yeah, reading's sending a lot of good resources. I might even link this onto the slide later on, just so you all can review it as well. So yeah, I'll do that after today's lecture. I'll add all of these screenshots to our slides. And actually, since I'm recording, so I'll send this problem in the chat as well. I'll take a screenshot, and that way you guys can work on this problem. And I'm just going to quickly add some of the things reading sent. So and again, please let me know once you're ready to move on. Okay, yeah. Sorry, let me just add this one last thing. Okay, I think some of us are ready to move on. And just for the sake of time, yes, you can see the answer here. Let me share. Okay. So our area should be 3 pi over 2. And our limits of integration are when r is equal to 0. So when we set our function equal to 0, that's how we can get our limits of integration. And let me see, I think okay, maybe I didn't send, or maybe I didn't link the picture of the graph, but let me just graph it for you all right now, just so we can take a look at what this graph looks like. So it's 1 plus cosine theta. Let me change to my polar form. So r equals 1 plus cosine of theta. I believe that's what it is. So we can see we have a limacon, I think that's how you pronounce it. And we want to find the area for one of these areas. So one complete loop. So if we set our r equal to 0, let me see this. Now that, yeah, that doesn't really help. But basically, if we set our r equal to 0 and we think what terms or what values of theta will give us 0. So if we set r to 0, then basically cosine of theta equals -1. So here, let me write it out. So we want to find where cosine of theta is equal to -1. And okay, let me see. Hopefully my trig isn't failing me. So when cosine of theta is -1, that's when we have theta is equal to pi. And yeah, I believe that's only one from 0 to 2 pi. So let me review what I put here as well. So yeah, actually it was a bit of a red herring for asking about where r equals 0, because if we just recall our graph, technically it's just from 0 to 2 pi. It doesn't do anything strange like overlapping multiple times or things like that. So we can just go from 0 to 2 pi. And if we trace it out, we start here at 0 and then we go here to pi. And then once we're at pi, that's when we get the first half. And then this next half is from pi to 2 pi. And so you can either just take the integral of the first top half and multiply by 2, so 0 to pi. Alternatively, you can go from 0 all the way to 2 pi. So both of these will give you the same answer. So let me double check what I put. So yeah, here I just literally plugged in 1 plus cosine theta, and here our limits of integration, I just chose from 0 to 2 pi. And then once we expand our integrand, we will get this, we eventually will get this expression. So the reason I was hinting about cosine squared of theta is because we don't really have a way to integrate cosine squared of theta unless if we use our double angle identity. And actually, is that wrong? Or, oh no, yeah, here I just split it because of +1, and then I added it to here. So yeah, sorry, I probably should have shown more steps, but hopefully this is just refreshing our memory of the different steps we take to get to our integral. And then here, hopefully, if we have practiced our integral skills, we should be able to get our final area. And then I just want to touch back on the idea of setting r equal to 0. So again, this was a bit of a bad example since our limits of integration didn't really matter. They weren't really affected by when our function is equal to 0. But just to give you an idea of when it would matter, so if we have, let's say, this rose shape, so let me try to draw it well. Let's say something like this. And maybe I ask, okay, what is the area of just a single petal? So in this case, our limits of integration isn't just 0 to 2 pi. We would have to be more careful of when we are actually going through the origin. So hopefully this is also just refreshing your memory on why it's important to be paying attention to our limits of integration. Okay, so that was a bit, and hopefully are there any questions as of now, or are we doing okay? Because our next topic is just using two polar curves, so we're using the same ideas, same formulas. So you can see here we're basically just using the area equation twice. So you can see if we had separated this integral into two separate integrals, it's basically we are taking the larger area and subtracting the smaller area. And if we think back to in our Cartesian plane, when we have to take our, or when we need to find our area of the intersection between two functions, we do a similar idea where we take the top function and subtract the bottom function. So hopefully that is just making another connection there for you all. Yeah, so as I mentioned already, we're just subtracting the inner curve from the outer curve as areas. And then one more time, just make sure you're finding the limits of integration. And this time, instead of finding where it goes through the origin, or I think in polar coordinates, the term is pole for origin. Yeah, so just you may see that being used as well. So the pole / origin. And yeah, so when we want to find our limits of integration, we can set our two functions equal to each other. So for example, in this diagram, if the pink function is equal to the blue function, we will get these 2 points where they are intersecting with each other. Okay, so hopefully this wasn't too much of a stretch. And yeah, that's a very nice picture that reading sent. So if you're confused about how we got to the 1/2 cosine 2 theta, please review that. Okay, so hopefully we don't have too many questions. Or of course, if you have questions, please do ask. But I think we are getting the hang of it. I don't think we have that many confusions. So if we're ready, let's try to solve this problem. So I believe you shouldn't need a calculator for these sample problems that I have. However, on the AP test, there may be some calculator active problems for polars. I think readings, typing in the chat, maybe. Yeah, okay, that's interesting. Because I actually haven't taken the BC test yet, so I'm going to be taking it with all of you. And yeah, okay, so again, please try to attempt this problem if you can. So we have two polar curves. We have the first polar curve, r equals 2. So this is our inside polar curve. So the question, how I phrased it, it's already giving you a hint of when we use our area formula, which one are we subtracting. And then our second curve is 2 sine of theta. So I'm not sure how all of you learned the BC topics, but my teacher, how he taught it, we had to draw by hand, or at least a basic sketch of these basic functions. So hopefully you guys at least have an idea of what these should look like. So that would be the first step. If you can graph it, that will help you to double check if your answer is reasonable. And then we can use algebra to set the two functions equal to each other and find our limits of integration. And then yeah, just make sure we are remembering the area formula, because although it's similar to our area of Cartesian planes, it's a similar idea, it's still not exactly the same, so we just want to be clear. Okay. So again, please update me as you're going along so we don't waste too much time. Yeah, too much of everyone's time. And yeah, because reading's sending a lot of good content, I just want to add it to my slides so future people can learn from those pictures as well. Yeah, so if any of you need a hint, so our first step would be to graph it. And yeah, so this sine function, when we have r equals something sine, it's a circle just not centered at the radius. So for sine, we would have, I believe, something like this for positive sine. Hopefully I'm not making a dumb mistake. And then we also had our r is equal to 2. And that, I believe, should look something like this, if I'm remembering correctly. And so once we get a basic idea, so what we want to find is inside of the r equals 2, but outside of the r equals 2 sine. So we want to find this area pretty much. And then so our next step is to find our limits of integration. So let me think, am I doing this correctly? I think so. Okay, yeah, so when we do r, so we want to set r1 equal to r2. So our r1 was 2, our r2 was 2 sine theta. So now basically we want to find when does sine theta, actually I think, did I draw this wrong? Yeah, I think I did. It should just be a single point of intersection. So let me adjust that. Okay, we got some answers. And I don't remember the exact answers, so we'll find out together if you're right or wrong. Yeah, and let me just finish this thought. So, oops, what did I do? Okay. So we should only have a single intersection point. Okay, sorry, my drawings are getting worse and worse. But anyways, when we solve, we can see that our sine should be equal to 1, sine of theta. So that's when we have theta equals pi over 2. And, what happened to my, okay. Pi over 2, at least on 0 to 2 pi. And, okay, so I think, yeah, and as Sage mentions, make sure we recall that our area formula is 1/2. So don't forget the 1/2. 1/2 integral a to b of our function squared. Okay, I think most of us, or at least some of us, have gotten the answer, at least a answer. So let's see if we got it correctly. So yeah, this is what I was trying to draw earlier, and I misremembered. We don't have 2 points of intersection, we just have 1. Okay, so our area should be pi, unless if I made a mistake. So if you guys catch something that I did wrong, please let me know. But how I thought this through was, and again, since we only have 1 intersection point, it's a bit of a red herring again to find our limits of integration. So I apologize, I'm not picking the best questions. But again, the times we would care about our limits of integration would be something like this, where we have multiple intersection points. So maybe something like that. So in this case, we want to be more careful with our intersection points. However, we just got a bit lucky with the problem I chose, because sorry, I lost my train of thought. Oh yeah, I think I was talking about the limits of integration, right? Yeah, so in this case, we can still go from 0 to 2 pi or 0 to pi, and we shouldn't have any problems. Okay, wait, so Sage said for the last equation in the top half, 1/2 instead of, I think here, what I did, I factored out this 4. So then when I factor out the 4 and I multiply with the 1/2, that's 2. Yeah. Okay, and yeah, just going over what I did here. Basically, I separated this into 2 halves, the top half and the bottom half. And that's just because the bottom half is easy to find out. If we just use our geometry, we can get 2 pi because we know our radius is 2, so 2, or so pi r squared. The total area of this red circle would be 4 pi, so just the bottom half is 2 pi. And then for our top half, we want to use our calculus and our area formula. So the outer function is our 2, r equals 2, and our inner function is our 2 sine of theta. So that's why I have 2 first squared minus 2 sine theta after squared. So hopefully this isn't too shocking. It's just plugging into our formula. Then once we simplify, so simplify, we take these exponents, we should get this, and then eventually we can get to 1 minus sine squared theta. And we can use one of our trig identities. So because of the, I forget what it's called. I think it goes by many names, but I think one name is the mother relationship. But basically, since we know sine squared plus cosine squared equals 1, we can plug in cosine squared here. And since we know our relationships, our special trig identity for cosine squared of theta, right here, we know that's 1 plus cosine 2 theta over 2. We can similarly plug that into here, so it'd be 2 from 0 to pi of 1 plus cosine 2 theta over 2. And then hopefully from there you guys should be able to, I think it's also called Pythagorean identity. I don't know why I said mother. I think mother equation. I think that's what my math teacher calls it. But anyways, Pythagorean theorem is more common, I believe. Okay. Well, I don't know. Do I have admin? Can I? Sorry. I apologize. I don't know who posted that. That's really unfortunate. I don't know if I have admin. Sorry. Maybe everyone block that person. I apologize again. That's really unfortunate. Sorry. Um, so I blocked that person, and I would suggest everyone please.
Hey, what just happened?
Okay, so someone sent a private image, so
Would you just send it to me or send it to like AP bot? Just send
okay,
it like ask when we need context. I'm like,
I'm not too sure how to do that. So what should I do? Um,
honestly, just DM me what you like the image, and we can probably give like an enforced punishment. Also, send them the Oh,
okay. Sorry, I'm in the middle of giving a lecture, so
yeah. I just want to make sure like everything's alright. Like I just got the ping.
yeah,
Hey! I just saw that.
yeah,
You're getting banned for that. You're getting banned for that, buddy.
yeah.
You're getting banned for
It's
that.
really bad. So again to the audience, I apologize.
Yes,
That
again,
was
we apologize. We
no,
are banning this guy right now.
yeah,
I
yeah.
apologize
Thank
for
you for
this.
banning him.
Yep, and
Yeah.
he's. Yep. All right, sorry for this. I'll let you go back to your
Okay,
lecture.
thank you so much. Yeah. So one more time. I'm really sorry. I don't know. Yeah, that's really unfortunate that that happened. Okay. Sorry guys. So let's try to get back on track. Just ignore that happened. Yeah. So using our identities, we should be able to get it into a form where we can take the integral. Okay, so any questions about solving this problem? Um, so again, just to recap one more time, I first just split this into two halves. The bottom half, um, we can use geometry. The top half, we can use our area equation. Okay. Yeah, so the reason I chose 0 to pi, so again, sorry about the intersection points. It's kind of a red herring because we don't actually really need it for our um, limits of integration. Yeah, so um, again, because I apologize, this isn't the best example to showcase when we would need our intersection points. So just in this case, since it only touches at a single point, um, so I guess technically what I could have done is from 0 to pi over 2, then pi over 2 to pi. However, just this singular point doesn't really matter much when we take the entire integral, so that's why I go from 0 to pi. And yeah, I guess that's an important thing to mention. Sometimes just the algebra, it's a bit hard to decide. Yeah, it's kind of hard to decide what the intersection points should be. So it's always good to try to remember the general forms. So the graphical forms of different functions. And yeah, pi over 2 is kind of a midway point. Um, well, so to kind of go back to the original question of why I choose 0 to pi, hopefully we can see, since from 0 to pi, I'm able to get a area of the red semicircle, the top, and then on the bottom, I'm able, or sorry, for this blue circle, I'm also able to get that area as well. So I guess I could have even just, or yeah, never mind. I was going to say we can just use geometry, but that defeats the purpose. And yeah, thank you. That person is banned, so that's good. Okay, yeah. So basically, what I'm trying to get to is, if the algebra can't really tell what's going on, try to graph it, and then that way you can visually get an idea of what is going on. So does that make sense? And also to give an example of when our, oops, not there yet, when our intersection points matter a bit more. So if we have, let's say something like this, and then maybe I have a petal here. So if I said I want to find just, okay, let me get a different color. I want to find this area. So now these are intersection points are more important, because when we only had a single intersection point, we could kind of cheat and just include it in our entire integral. However, now, since it's spread apart, we can't really do the same thing again. So our two choices are to take this integral and this integral to find the areas, or we could take the entire integral and subtract just this part. So hopefully this is clearing up any confusion. Is anyone still not clear about any of these ideas? Because if so, please let me know. I'll try to explain in another way. Yeah, okay, and yeah, thank you, Reading, for providing all of the wonderful formatting. At least I appreciate it, and I'm sure we all do. Okay, anyway, so if there are any more questions that come up, please let me know. But since we've covered polars, let's go back to the start. And so so what I want to ask is, are there any more topics that we want to go over by request, or are we okay just going through the first 6 topics in order? And so I'm not sure if that's a question about the bottom of 2 and inside 2 sine theta. Okay, yeah, so I'm just going to go in order. We don't have that many. I mean, unless if there's really a specific topic that we want to go over. Okay, I think it's all right. Let's just go starting from the first topic, and we'll move our way backwards. Okay, so coming back to parametrics. So of course we already used the idea of parametrics in our polar. So now we're just taking it back a step and focusing just on the parametrics. So to review parametric equations, they define curves using 2 separate equations. We have one for our x and one for our y, and the parameter is t. Most of the time that represents our time. And then to find our derivative, So that also means the slope of our tangent line. In the graphical sense, we can use this formula. And if you recall, it's the same as our... Oh, is my screen not working? Can... Okay, so can anyone else not see it? Okay. Yeah, so Pikachu, I apologize, but I don't think there's anything I can do on my end. Yeah, so maybe try to restart restart your computer or something. Yeah. So again, sorry, but I don't think I can do anything on my end. Okay, so good luck with your end. Anyways, yeah, so this is our form for our derivative of the parametric equations. And as I was mentioning, this is similar to our derivative of a polar. And the reason is because we got that equation from this equation. So this one actually came first. The only difference with the parametrics was our parameters in terms of theta instead of t. And then one more thing, of course, for this formula, we can't divide by 0, so we just always want to make sure that our dx dt isn't equal to 0. But regardless, most of the time, you don't have to look for this condition explicitly, because if you try to plug it in and it's over 0, then you probably did something wrong. And okay, I don't know. I think parametrics and polars are both unique in their own ways. Parametrics is kind of a prerequisite for understanding polar, because there's a lot of applications of polar that build on parametrics. Anyways, just my 2 cents for the conversation in the chat. Okay, so again, our derivative gives us the slope of the tangent line, so that's our graphical, what's the word I'm looking for? Graphical representation. And yeah, I'll hope for you as well that we have parametric, not polar. Anyways, okay, let me see what else am I missing. And yeah, so basically these last two. So the first point is just we use parametric most of the time when we can't write a function simply in terms of y equals f of x. And yeah, basically any derivative rules that we have, we can apply to parametric functions as well. And finally, we must have a smooth enough curve for dx dt and dy dt to exist and both be continuous. So that's just one more thing to pay attention to. However, I think most of the time these conditions should be a given. And yeah, the formula for arc length, you should know that. And we'll go over the formula as well in a few slides. So hopefully we will review that soon. Okay, so now we have a sample problem for parametrics. Our x is defined by t squared plus 1, and our y is in terms of natural log of t. So let's all try to find dy dx at t equals 1. And then again, some hints. First, let's find the derivatives in terms of dt. And again, also make sure our dx dt isn't 0, but I can tell you for this problem it shouldn't be. Yeah, and thank you, Reading, for helping us out with the arc length curve. So again, let's all try this problem and let me know once you have a solution and you're ready for me to move on. Okay. So to do dy dx in terms of x, so I think for that question, I mean, there's nothing wrong with keeping it. Yeah, so I don't think there's anything wrong with doing it in terms of x. However, it's probably better practice just to keep it in terms of t. So 2 reasons. These are just my own personal reasons. One, because it shows you're still working with the parametrics, because if you change it back to x, that might it just might be confusing for the grader or for whoever's looking at the work. And another reason is also that sometimes you may not be able to plug in x perfectly, and I think it's a better use of time to just keep it in terms of t and move on rather than trying to, you know, um, what's the word? Not simplify, but manipulate the function in order for you to plug in x. So that's just my opinion for that question. Hopefully that helps. And okay, we've gotten some answers, so let's take a look together. And yeah, so what I got is 1/2. And the reason or the work I did to get there is first I took my dx dt, so derivative of x in terms of t, so that should be 2t, and then our dy dt is derivative of natural log, so 1 over t. Then we can take our dy dt, divide by dx dt, excuse me. So we divide, we should get 1 over 2t squared, and then we plug in 1, we get 1/2. And yeah, so King, Colin, good job. You showed the correct work. You got the right answer. Okay. And congrats to all of you who got the right answer as well. All right, so now the second derivative of parametrics. So we want to first remember what our first derivative is. So again, just a recap, recall. This is our formula. And then our second derivative is this formula. And so do we all know why we need to divide the dx dt? Just curious if we remember. If not, I can go over, but I just want to see if we can recall. Okay, we're the 2t squared. I believe when we do the division, it was 1 over t divided by 2t. So we just combine we combine the two denominators. We should get 2t squared. Yeah. And again, just to ask the question again, does anyone recall why we have to divide the dx dt for this formula here? Just, okay, it's all right if you don't. I'll explain as well, but okay, yeah. So actually, just to finish this slide, so real quickly again, remember our second derivative tells us about concavity. So positive second derivative, we have concave up curve. Negative second derivative, we have a concave down curve. Okay, I just wanted to get this slide finished. So let's come back to the idea of why do we have to divide by dx dt. So let me use my whiteboard. So we know we have our second derivative, dy dx. So to take our second derivative, we of course need to differentiate our first derivative. So if we differentiate dy dx in terms of t, so now this is basically our chain rule. So if we think of dy dx in terms of, let's say, I don't know, just making this up, let's say dy dx is equal to f of x. So just so you can see, because dy dx in itself is a function, so if we take the derivative of f of x in terms of d dt, what we would get is f prime of x. And so we can't just leave it here, because x itself is also a variable. Okay, and okay, yeah. So some of you are saying that we don't have to know this, and that's partially true because there's honestly not that many applications of the second derivative for parametrics. Most of the time, they just care about the first derivative. But again, let's just quickly go over this just in the, if we all get unlucky and we get a second derivative question on the BC test, I think it's still good to go over. Okay, yeah, so coming back to this, as I mentioned before, x itself is a function. So in order to satisfy our chain rule, we also need to do the x dt. So hopefully you can see this format is similar to our format here. So we can first take the derivative. Yeah, again, it's on the CED. I think so. For those of you whose teacher said it's not needed, I think what they really mean is it's super rare. Just because if they ask for it, it'll just be what is the second derivative. It won't be like the first derivative where there might be questions about. Well, I mean, I guess they could ask about concavity. Yeah, so again, it's just less common than the first derivative. That's all. Okay, let's come back to this proof again. So using this similar structure, we can first take the derivative of dy dx in terms of x. So that's our second derivative here. And then remember, x itself is a function in terms of t, because t is our parameter. So what we have to do is apply our chain rule. So multiply by dx dt. However, all we want is a second derivative. We don't want this dx dt part. So that's the reason why if we divide our dx dt, then these two cancel and we're just left with our second derivative. So if we come back to our original formula, that's the reason why we have to divide our dx dt. It's because x itself is a function, and we're not differentiating in terms of x, it's in terms of t. And yeah, and reading has also sent a very nice proof as well. Yeah, so the idea again is all coming back to chain rule. So because of chain rule, we have that extra dx dt, so we want to divide it out. Okay, hopefully that made sense. Yeah, so it's pretty cool, but if we excuse me, if we just simplify it in terms of basic ideas, then sorry, what was I thinking? Oh yeah. So once we simplify to the basic ideas, it's just chain rule pretty much. Okay, so everyone, let's try to solve this problem. Given x of t equals sine of t and y of t equals cosine of t, let's find dy dx, and then also try to find the second derivative. And let's do both of these. Or actually, if you don't have time, it's okay. We don't have to plug it in, but or actually for the second derivative, it may be better if you plug it in. So I don't know. It's up to you if you want to plug it in. But the skills we're trying to practice is taking our derivatives. And yeah, so everyone, let's attempt this. Tan of 0.25 pi. Okay, Pikachu. I'm not too sure if that's but maybe, yeah, I'm not too sure if that works, but just go ahead. Maybe that's an alternative way. Yeah, reading, that's a very ominous looking chain rule there. And oh, okay, sorry, yeah, Pikachu, I see what you're doing now. Yeah, I think that's but is there a 0.25? Oh, okay, yeah, but yeah, right, Pikachu. Sorry, I just didn't realize that you were already at the answer. I thought you were still just taking the derivative of y or x. Sorry about that. Okay, anyone else need more time, or? Okay, I think, okay, let's go over the answer, but real quick, let me also add, oh, okay, yeah, well, so the answer is out. Yes, it should be negative 2 square root of 2, if I did it correctly. I just always want to emphasize that I did these problems myself, so it's always possible I made a mistake. Okay, let me quickly add this. Let me add it a new slide. Okay, back to the solution. Yeah, hopefully I didn't make a mistake too, Sage. But But again, I'm pretty confident in myself, but if any of you spot a mistake, please let me know. Yeah, again, our main ideas, of course, are to first take our dx and dy's in terms of dt. So very simple, we know our trig, derivatives, hopefully we do. Then we can divide these to get our tan, so our uh, first derivative would be negative tan of t when we divide. And yeah, I guess I didn't plug it in here. So yeah, if you plugged it in, hopefully you plugged it in right. Okay, and then for our second derivative, we want to use our formula where we first take the derivative of our first derivative. And so here we have negative secant squared t. And then we have to divide our dx dt. So cosine of t. I think that should be cosine of... Oh, sorry, wait. What did I do here? Or am I confusing myself? Yeah, dx dt. Yeah, I think I mistyped it, right? It makes more sense to be cosine of t. So I think I just typoed it. And let me see, does this make sense if I... Yeah, I think that makes more sense, right, guys, if I put in cosine. So let's see if that makes sense. So divided by cosine of t, because that's my dx dt. And plugging in pi over 4, we get negative 2. And then for cosine pi over 4, that's square root of 2 over 2. Yeah, so that should be right. And then we just divide these two, and we should get... Uh-oh, why did I put negative 4 square root of 2? Okay, I don't know what I did there. Oh, no, it should be the same thing. Yeah, negative 4 over square root of 2. I just didn't simplify it down, but those two should be equivalent. So hopefully we understand the solution. Again, just recall what our formulas for the derivatives are, and I just want to emphasize one more time for our second derivatives, don't forget the chain rule part. Yeah, so just remember it, and then we should be good to go. Okay. Now to arc length. So I think I had a... Oh, so I think that's negative 4 divided by square root of 2. And unless if I'm making dumb mistake, I think those two should be equivalent. Okay. Yeah, because... Here, let me just prove it too, just so we're all have a conclusive answer. So if we do 4 over square root of 2, that equals 2 times 2 over square root of 2. 2 divided by square root of 2 is square root of 2, so yeah, it should be 2 square root of 2. Does that make sense? Yeah, so hopefully I didn't confuse anyone too much. Those two should be equivalent expressions. Okay, cool. Let's move on to arc length. So again, I think I had a question about arc length. So we're going over it now. Right, so again, remember what our parametric equation, what the format is. We have a function for x with the t as a parameter, function for y as with t as a parameter. And then for curves, so now we're focusing on curves, we also have some bounds. So maybe from A to B. And yeah, so arc length you should, so let me phrase it this way. If it's an FRQ problem and they don't give you calculator, you probably should be able to do arc length. However, wait, actually, am I confusing this with something else? Well, no, I think you should be able to do arc length. Yeah, as reading says, it depends. So for example, if like these are just single numbers, you should be able to plug in easily. Or even if it's like 1 plus cosine square, you should be able to use some trig identities. Yeah, so what I was trying to say earlier is I doubt College Board is going to give you a super, almost impossible integral to solve by hand. I'm sure they should, if they want you to solve it by hand, they should give you an easier one if it's, and I think it's, yeah, it should be fine to use exact answers. aren't parametrics on the calculator section. Yeah, I'm not too sure. Maybe if reading you can answer these questions, just because I haven't taken the BC test either, or if anyone here has taken the BC test or has done research. Yeah, if someone could let us know, that'd be great. Yeah, so I guess they're on calculator too. Interesting. Okay. Well, anyways, let's just come back to this slide. Sorry for digressing, everyone else. So our arc length, so most of the time it's given by a variable capital L, is given by the formula dx dt squared plus dy dt squared. And this formula, we can derive it by using our Pythagorean theorem on infinitesimal segments of the curve. Yeah, I can't really pronounce that. Yeah, but basically we're just doing very small Pythagorean theorems and then summing them all together. And then one more thing, we just want to make sure that our dx dt's and dy dt's are continuous. And yeah, that should be our only condition for arc length. For the Maclaurin series, here, let me first finish this slide, and then I can answer that question. So again, just to reiterate the idea of Pythagorean theorem, if we have a curve and we use Pythagorean theorem on small intervals, so maybe here to here, we have a small triangle here to here, another triangle here to here, another triangle, so on and so forth. So we're getting all of these small hypotenuses, or whatever the plural of hypotenuse is. And then you can see if we just take the integral, so if you recall, since integrals are based on Riemann sums with the limit, so we're basically taking the limit of all of these Pythagorean theorems, and then that's what gets our arc length. Okay, so hopefully we understand where we get this formula from. If so, let's try to solve a problem. So here's a sample problem, and yeah, so this one I think it's hard to solve with a solve by hand. So yeah, if you want, for the sake of time, you can just keep it in integral form, and then we can just look at the integral form together. Okay. Yeah, so again, everyone, let's try to solve this. And then just let me know once you're at the integral part. Well, actually, yeah, then it's kind of just plugging in. But just make sure you remember the formula, and let's move on. And let me... Sorry, I haven't been keeping up with the chat. So for the MCs, so my understanding is most MCs they don't release, but FRQs they typically release. And then yeah, I think College Board releases some MCs to the teachers. So if you have a AP teacher, yeah, MCs aren't supposed to be released to students, but I guess somehow maybe teachers release them. If you search hard enough, you might be able to find online. And yeah, FRQs are pretty much always released. Okay, I'm just going to show the answer because this is more of an exercise if you remember the formula and if you can plug into your graphing calculator. So yeah, if we just, yeah, so we first take the derivatives of dx, dt, and dy dt, then we can plug into our formula. So 1 squared plus 2t squared. In other terms, that's 1 plus 4t squared. Yeah. And then our bounds were from 0 to 2. So once you plug that in, you should get 4.646. So hopefully I plugged that in correctly. Yeah, okay. Seems Pikachu agrees with me. Okay. All right, so let's move on to vectors. So a vector valued function has this form with these, I think these are brackets, these, yeah, actually I'm not too sure what they're called, but just these kind of bendy things. So we have x, y, and yt. Okay, and then, so these vector valued functions, most of the time they are related to motion problems. So our derivative, we would just take the derivative of our x component and the derivative of our y component. And then the magnitude of our velocity vector, that's our speed. So to find that, we can use our Pythagorean theorem of these two derivatives. And then that gives us our speed, which is the magnitude of our velocity vector. And then if we take the second derivatives, we will get our acceleration vector. And so just a few things that I want to point out. This magnitude, just remember that it's Pythagorean theorem, and that way it shouldn't be too hard to remember. And then since this is similar to the arc length equation, just make sure you are understanding the difference between the two. So arc length is literally this, just with our integral. So that's just an interesting connection. And yeah, and then this picture is what my calculus teacher showed me when he was explaining the difference between vectors and just simple coordinates. So simple coordinates are just a point on our plane. But vectors, these are actually the kind of the ray or the direction. I forgot how he explained it, but hopefully this picture gives you an idea. It's not just a point, it's also, it's more of that direction and that magnitude as well from the center. And yeah, hopefully this visual also helps you to understand the difference between coordinates and then also vectors. And yeah, that's also one important thing to keep in mind. If it doesn't say that it's a vector, then it likely is the coordinate. So just be careful of what they're asking. If they're asking for the vector form, they will say we want, they will mention vectors somewhere in the problem. In that case, you want to use these brackets. Okay, yeah, I think if that's what AP Classroom calls them, I'll call them brackets as well. So yeah, again, vectors, make sure we have the brackets. If not, just use our standard standard coordinates. Yeah, and as reading, so reading is saying vectors are directed line segments, both direction and magnitude, unlike scalars. So yeah, so vectors, in my experience, I think they're more in physics and things like that. In calculus, we just have a brief overview. And okay, so let's try to solve this problem. We have a position vector, so t4 over 4, t to the power 5 over 5. So try to find the velocity vector, the speed at t equals 1, as well as the acceleration vector. And again, so some hints. Remember, we're just taking the derivatives of our x and y separately. And then yeah, just remember, what is our formula for speed? Hint again, it looks similar to arc length, but it's not exactly the same. And yeah, my worst nightmare was just mentioned. Is that a Despicable Me reference or something else? Because I know in Despicable Me the villain is called Vector, but anyways, that's kind of a digression. Or yeah, I don't even know if that comment was meant for. Okay, anyways, sorry, I'm just digressing here. So again, let's try to find our velocity vectors, our speed, and our accelerations. And it's almost approaching 1 hour 30 minutes. So do you want to try this on your own, or should I just go over the solution now? All up to you. So Sage, when you say yeah, does that mean you want to do on your own, or? Okay. Yeah, no problem. Everyone, let's just try to solve as much as we can. And yeah, we're almost there. Just 2 more topics after this one. And yeah. Okay. So I hope you all don't mind. I'm just going to show the answer now. So hopefully we can at least see if our yeah, I guess I should have put you don't really need to show that much work for this one. As long as you know how to take your derivatives, you should be fine. Lecture for unit 10. I'm not sure. Actually, let me just check for you on the lecture slide real quick. So again, if you go to this link that I sent earlier, so let me see, Unit 10. Okay, so I think reading is teaching that on 5/4, 1 p.m. Eastern time. So maybe look out for when he makes the event on Discord. Um, yeah, so hopefully this helps. Keep an eye out for that. And yeah, okay, let's come back to this question real fast. So our velocity vector should just be this. Our speed, if we take our Pythagorean theorem, we should get square root of 2. And then acceleration vector, if we take our derivative one more time. Um, oh, uh, oh yeah, Pikachu. So I think that's, oh no, you're all good. Um, yeah, so you just didn't plug in the 1, but that should be the general um, formula for speed. So, okay. So hopefully that wasn't too bad. Let's move on. So now integrating vector value functions. Okay. And so again, similarly to how in polars and parametrics, we can reuse ideas from previous topics. For vectors, we can also use our integrals of real valued functions. So just to give you a refresher, that's when we have some initial position and then a velocity. Then we want to find a new position. So these concepts are kind of touching on particle motion, so displacement, initial position, final position, think concepts like that. So now we're just applying them to our vectors. So you can see here, when we want to find a new position vector, we can do our real value functions integrals for both the x and the y. So again, a refresher, that's just if we have our initial position plus the displacement, and the displacement is just our integral of velocity, we can get our final position. And okay, yeah, hopefully, sorry, did I miss any questions? Uh, oh yeah, the question was, why did I plug in 1 for speed? That's just because I asked for t equals 1 for the speed. I could have asked what is the velocity at um, t equals 1. So in that case, you can just plug into 1 and get your velocity vector at 1. Yeah. So it's nothing special about speed. It's just whatever the question is asking. Okay. And let me see what else here. Yeah, so again, this is just the same idea as initial value problems. We're just using both our x and y's for vectors. Okay. So let's try to solve this problem now. So we have a particle with velocity vt equals 2t for the x and cosine t for the y, and also an initial position of 1, 0. So we want to find what is our position vector. And so again, one hint is just to do initial values, first focusing on the x, and then you can focus on the y, then put them together. So yeah, I have to use the bathroom, so sorry about that. I'll be back in a minute or so, so try to solve this problem, and then let me know in the chat once you're ready. All right, so I'll be back in a minute. Okay, so I'm back, And let me see, did we get yeah, I think Roja, that should be the right answer. I just realized I never asked for a final position, so that's kind of my bad. But anyways, if you find the general form, if the question asks, what is the velocity at, or sorry, what is the position as time equals 3 or whatever, you can just plug in and you should be able to get your answer. And yeah, so I think we got this. T squared plus 1 plus, not plus, t squared plus 1 comma sine of t. And so again, these are just our initial value problems. Hopefully it's not too new because we've done these types of problems in previous units. Hopefully it's just more of a review and then putting these ideas together with vectors. And okay, so hopefully no questions there. And then let's move on to our last topic of today, which is solving motion questions with parametrics and vectors. And yeah, this is kind of more a review of what we've already done. We're kind of just putting everything together. So with our derivatives, we can find our velocity vector, which is in this form. We can find our speed, which again is our Pythagorean theorem. We can also find our acceleration vectors. And for displacement, we can find either just subtracting the initial versus of the final minus initial positions, or we can take the integral of our velocities. So for the vector form, we would just do this for x at first and then for y. And then again, remember our arc length is this formula. Yeah, so because v of t, well, yeah, so this is more distance traveled, so it's a little bit similar to arc length, but just remember we have our other arc length formula as well. Yeah, this is the original distance traveled formula from the previous units on particle motion. So hopefully this makes sense, because yeah, our total distance is our speed just compounded over time, so that's our absolute value of velocity. And yeah, as Viper is explaining, those two should be equivalent, so this should be equivalent to our other equations for arc length. Okay, and yeah, so then let's try to end off strong. Let's try to solve this problem. So we have a particle moving with this velocity and initial position. So find the position vector, and then also find the displacement from 0 to pi, and then finally the total distance traveled from 0 to pi. So let's see if we can solve this problem. And then this will be the last problem of the day. So again, let's try to finish strong. And yeah. And let me just so how would we deal with parametric polar question? So I'm not too sure what you mean, but polars and parametrics, they are very similar to each other, especially in terms of the derivatives and things like that. Sorry, I'm not really sure if I understood the question about the parametric polar question. So maybe if you could rephrase it. Yeah, sorry about that. Okay. And yeah, sorry, I just wanted to double check and make sure we covered all the content that I had planned for today. Oops. Okay, well, you guys already saw the answer, but again, make sure you know how to get there. Yeah, so we did polars already, so I think that should be it. And anyways, I'll post the slides as well for all of you. Okay. So, yeah, sorry, I kind of already released the answer. So let's just go over it then. So our position vector, if we take our integral of the velocities, we should get this, I believe. Or no, I think for this one it should be negative cosine t. And okay, so this is my mistake. Yeah, I think what Pikachu said, that's right, because our initial displacement should be 0. And then displacement from 0 to, so let me see, the displacement was from 0 to pi. So if we find what is pi of the x at t equals pi, that is 0. So 0 to 0, displacement is 0. And then our negative cosine of pi, that's negative 1. No, that's just positive 1 because the two negatives cancel out. And then so from 1 to, oh, oh yeah, from, wait, did I make another mistake here? Because from 0 to 1, that should just be 1, right? Uh, sorry, for Viper, is that a question for me about the no distance traveled, or? But anyways, did I make a mistake here? Because our, I think I did because I had the plus 1 initially. I believe it should just be 1. And yeah, so if we take the distance, we have sine squared plus cosine squared. So that's our Pythagorean identity. So we can just substitute that with 1. So when we take our integral, it should just be pi. Oh, okay, okay. Yeah, I just wanted to make sure that I wasn't missing any questions. Okay, so is everyone fine with this answer? Does it look correct? Because if so, that's all I have for today. So again, let me just share these links again from the beginning of our lecture. So if you could fill out this form, lecture feedback form, I would greatly appreciate it. It would help me out a lot. And if you want to see our future lectures hosted by 5 Hive, you can find the all the lecture information there. And then also keep an eye out on the events here in this channel. I think periodically we're going to be adding new lectures. So yeah, make sure you keep an eye on that. Let me see, is there anything else for you all? And yeah, by the way, that 5 Hive lecture schedule 2025 spreadsheet, I'll be linking my slides and recording there as well. So in a hopefully in a day or so, you should be able to see that. Yeah, so no problem at all. It's my pleasure for teaching you all. And let me see, is there anything else? Yeah, so I sent this formula already. Not formula, this link. Form, that's what I was thinking of, this form already. And let me see. So any other questions from you all? Yeah, so hopefully now that we covered this, you are better off. So how was my day? My day was okay. I'm pretty tired, but I'm doing good. Okay. Are there any other questions? If not, I'll end my recording. Because if we have any other questions, so I guess not. So let me end my recording now. And